Okay, section 6.2 is what's called partial derivatives. So our objectives are to find the partial derivatives of a function, evaluate partial derivatives, and then find the four second-order partial derivatives of a function in two variables. So our vocabulary is obviously partial derivatives with respect to x and y, and then this thing which is called a Cobb-Douglas production model. So what exactly is a partial derivative? Does that mean we're only taking part of the derivative? Well, not exactly. What it actually means, and we'll show this in a second here, is that if you've got something which is affected by more than one thing, so again, you've got something which is affected by, let's just say, two things, and we assume that one of those things is actually held constant for a while. So, like maybe the example that I kind of mentioned to you in the last section with the weather, let's assume that maybe that the temperature outside is 50 degrees, but there's a bunch of wind, and the wind actually makes it feel, with the wind chill, it actually makes it feel like it's 40 degrees. Well, let's just assume that the temperature holds steady at 50 degrees, so we can then take a derivative to find out what is the wind chill doing at an instantaneous point in time to actually affect how it feels outside. Or we can say, okay, now if we know that there's a constant wind, like the wind is blowing at a certain rate throughout the whole time, we could hold the wind chill constant instead and say, oh, okay, maybe there's a 10-mile-an-hour wind, but we're going to say, what happens to the temperature or the wind chill factor now if the temperature starts to increase or decrease? So the temperature would change, but the wind chill would hold constant. That's kind of the idea behind a partial derivative. Algebraically, not really that difficult as long as you're just being careful. All right, so let's consider the function z equals f of xy, where the function is x squared y cubed plus xy plus 4y squared. If we temporarily fix the y to be 3, so no matter what happens with x, y is always going to be 3 in this case. That just means we're going to plug 3 in for all the y's, simplify it, which is what you see here, and then we could go ahead and take the derivative with respect to x just as we normally would, and you would get 54x plus 3. So the main idea behind partial derivatives, again, not that challenging to do. So you're actually replacing y with a number. Well, instead of actually replacing y, we might just leave the y in there in general. So you just have to think of y when you take a partial derivative with respect to x. You have to think of all other variables as constants. So don't think of them as an actual variable. That's the hard part, is you're going to have to really, again, you're going to have to be careful and see that. So the notation is a little bit different. Notice that the derivatives here and these notations look a little bit different. The d's no longer have the extra little tail on the bottom right-hand side. So when you draw a partial derivative, instead of drawing it like this, you actually draw it almost kind of like a backwards 6. There's no tail. Very important that you actually make that distinction, because if you draw one with a tail on it, it's going to be an actual derivative, which is different than a partial derivative. So it'll take some getting used to. Just draw a backwards 6. That's the way I tell people to do it. It's the easiest way to think about it. Okay. If you want to take a partial derivative with respect to x, you can write it in a couple of different forms. Like you saw here, I can write the derivative of the function, or f, with respect to x. Or since we're talking about a function of xy, and typically we can call that z, just like f of x is the same as y, we can call a derivative, f of xy, z, so we can write it as dz dx. Or another notation is this little sub feature right here. That little sub x on the f means you're going to take the partial derivative with respect to x. In other words, x is the variable, y would be constant. Or in this case, right here, that one would be the partial derivative with respect to y. So y would be the variable and x's would be held constant. Okay, so if we were to take the derivative of, and we're going back to the same one that we started with right here, if we were to take the derivative of x squared y cubed plus xy plus 4y squared with respect to x, That's what that means, the partial derivative with respect to x. We treat y like it's a constant. So basically, you just take the derivative of the x squared part, so which is 2x, and then multiply it by the y cubed. Again, the y cubed is not really anything we're going to treat like a variable because it's with respect to x. So in the second part, xy, while that looks like it's, again, it looks like it's a product rule, it's not, because we're holding y constant. So the derivative is just the derivative of x, which is 1, times y. And then the last part, which is even nicer, 4y squared, the whole thing here we have to treat like it's a constant. So the derivative of any constant is 0. That's why it goes away. And then the next one, we're going to take the derivative of exactly the same function we just started with, but now we're going to do it with respect to y instead. So this time, we hold the x constant, and we just take the derivative of the y cubed. So that's the 3, right out in front of here, y squared, and then the x squared, we just put that in between because it's alphabetically in the correct order. So then we'll take the derivative of xy, which is just going to be the derivative of y, which is 1 times x, which is right here. And then in the last one, it's 4y squared, so then you just take the derivative of 4y squared like it was anything else, which is 8y right there. Okay, so obviously it can be challenging to look at a variable and think of it as a constant. Just remember back to when you were in probably Algebra 1 for the first time. It could be difficult to look at a letter and think, oh, that could be a number. It's kind of the same idea. We're just kind of going backwards with it. Your book does a good job of using colors and stuff on page 534 if you want to look at that as an extra reference. But I think you'd be able to handle this. All right, so the definition for z equals f of xy, the partial derivatives with respect to x and y are given as dz over dx against the backwards 6 d's is equal to the derivative of f of xy, and dz over dy is equal to the derivative with respect to y of f of xy. So for our example 1 here, we're given f of xy equals 3x to the 2y plus xy squared. We want to find f of x, f sub x, which is the partial derivative with respect to x, right there. And we want to find the partial derivative with respect to y. So let's start off with the first one. Partial derivative with respect to x. Now remember, we have to treat y like it's a constant. So in the first one, that exponent right there is just a constant. So we just treat it like a constant. So what would you do if you had 3x to some power? You would bring the power out front. So we're going to multiply 2y times the 3x and then reduce the power by 1. And then the second part, xy squared. Again, remember the y squared is like a constant. So the derivative of x is just 1. So then that's just y squared. And I'm going to clean this first part up here because we have 2 times y times 3. So that's really 6y x to the 2y minus 1 plus y squared. And there you go. That's the partial derivative with respect to x. Let's try the partial derivative with respect to y. Now we have to treat the x's like they're constants. Okay, so now this is a little bit different. When you look at this first term, x being a constant means that you basically have an exponential function right there. It's not an e, it's an exponential function. So if you needed to place like a 4 in its place or something like right there, you could do that. It's a little bit more challenging. So let's go ahead and see about this one because I don't know that we've done an exponential derivative of this form. So the first thing is 3 stays there. That's just a coefficient. Now, x to the 2y. So the y part is the variable. So we're going to rewrite the function. X to the 2y. Normally we multiply it by the derivative of the exponent, which we are going to do here. The derivative of the exponent is 2. We also have a natural log of the base that we have to multiply this by. This right here might be something that we hadn't done yet. That part right there. So it's really 3 steps. It's rewrite the function times the derivative of the exponent times the natural log of the base. So this part right here might be something you hadn't seen yet. And that's just the first term. The second term is much, much easier to do because you're just taking the derivative of xy squared. So just take the derivative of the y part. So that's 2y, but we'll write it as 2xy because we keep the x as a constant. And that's it. That is the partial derivatives of x and y of that function. Okay, let's go ahead and do number 2. Again, really shouldn't be terribly difficult. Let's find, in this case, we're going to write it as the partial of x first. So the partial of x is going to be e to the xy times the derivative of the exponent. And again, remember, y's are constant now, so it's just going to be y, because it's like having 5x up there. There would just be 5. Okay, so that's the derivative of that part. Now the derivative of the second part, remember that y is a constant, so it's like having a 5 out in front of the natural log. So it's going to be y times derivative of natural log of x, which is 1 over x. And again, I'll just clean that up. So I'm going to move the first y to the front. And then plus y times 1 over x is y over x. Okay, now let's go ahead and do the partial with respect to y. So it's pretty much going to be the same thing for the first one. That's going to be rewrite it e to the xy. But now the y is the variable and the x is the constant. So we're going to multiply that by the derivative of xy with y being the variable. So that's just going to give us x. Plus, now this time the y is the variable. So the derivative of y is 1 and natural log of x is a constant. So it just stays there. And again, the only thing I'll do to clean it up is I'm going to move that first x out in front of the e. Other than that, that's it. That's done. All right, and then our last stuff down here has to do with this model, which is called the Cobb-Douglas production function. Its general form is P of xy equals capital A, x to the lowercase a, y to the 1 minus a. I know, the capital A and the lowercase a, why couldn't they come up with a different variable? I don't know, that's the way it's written. P is the number of units produced with x units of labor and y units of capital. Capital is the cost of machinery, buildings, tools. Basically, it's your supplies. It's the things that you need. And then the labor is obviously how much you have to pay for people to do the work. So the partial derivatives dp dx and dp dy are called respectively the marginal productivity of labor and the marginal productivity of capital. Again, labor is the x, capital is the y. So Mitel Cellular has the following production function for a smartphone. As you can see, it's 50x to the 2/3, y to the 1/3, where P is the number of units produced with x units of labor and y units of capital. Find the number of units produced with 125 units of labor and 64 units of capital. That's literally just plugging the stuff in. So that means P, so labor was 125, that's x. Capital is 64, that goes there. So we're going to do 50 times 125 to the 2/3 power, and then 64 to the 1/3 power. Believe it or not, these are things that I can actually do in my head. So that's going to be 50 times 125 to the 2/3 power is the cube root of 125, which is 5, squared, which is 25. And then 64 to the 1/3 power is just the cube root of 64, which is going to be 4. So it looks like we're going to get 25 times 4, which is 100, times 50. So that's going to be, what is that? 5,000? 5,000 is the number of units produced with the number of units produced of 125 units of labor and 64 units of capital. Now, if we want to find the marginals in part B, as it says up here, the marginals are just going to be the partial derivatives. So let's go ahead and do the partial derivatives. So the first one we're going to do is P sub x. and that's going to mean that the y part is held constant, so it doesn't change. So all we're going to do is take the derivative of the x part. We're going to bring the 2/3 out to the front and multiply it by the 50, which is 100/3. X to the reducing that 2/3 by 1 is now -1/3. And then y to the 1/3, because that just stays the same. So there's your partial with respect to x. Now we're going to do the partial with respect to y. Same general idea, but now this time we only deal with the y. The x part stays the same. So we're going to bring the 1/3 out front and multiply it by the 50, so we get 50/3. And then x doesn't change. And then the y part is going to reduce by 1, so subtracting 1 from 1/3 is -2/3. And there is the, those are the marginals. So now we want to evaluate the marginal productivities at both 125 and 64. So now let's see what we get there. And that's just plugging the marginals in. So it's two different ones to do, but it's not hard to do. So P sub x of 125 and 64 is going to be 100 thirds, 125 to the -1/3, and then 64 to the 1/3. This one might be a little more challenging. Let's see. 100 thirds. 125 to the -1/3. Well, the 1/3 power is the cube root, so that's 5. And then that just, the negative puts it as a fraction, so that's 1/5. And then again, the cube root of 64 is 4. So it looks like, let's see here, that's going to, 100 divided by 5 is 20, times 4 is 80. So I think we're going to get 80 thirds for P sub x. P sub y, again, same numbers, is going to be 50 thirds, 125 to the 2/3 power, and then 64 to the -2/3 power. So that's going to be 50 thirds times 125 to the 2/3. We've done that before. That's actually 25. 64 to the -2/3. So again, cube root is 4. Squared is 16, but we're going to have to make that a 1/16. And that will reduce a little bit. The 50/16 reduces to 25/8. So then I'm going to get 25 times 25 times 1 on the top, which is going to be 625. I'll have an 8 times 3 in the bottom, so that's 24. 625/4 is our marginal for y. All right, now interpret what those marginals actually mean. Well, basically what that's saying is, the first one, the P of x, means if we were to hold, let's go back up here, if we were to hold the production of the capital constant, the rate of change would be 80 thirds. So if we were to hold, in part C, if we were to hold, let me do this in blue, holding, keep losing my vocabulary here, holding the capital productivity, so holding capital constant at 64, 80 thirds is the rate of change of labor at x equals 125. And then exactly the same idea, I won't have to hopefully scroll back up and down here. This one will say holding labor constant at 125 625 over 24 is the rate of change of capital at y equals 64. And there you go. All right, and the last thing we have to talk about in this video is higher order partial derivatives, because just like regular derivatives, you can take second derivatives. It's done a little bit differently, and the notation gets a little bit strange, so you got to be careful. You can take second, third derivatives of partial derivatives of two or more functions. We're going to focus on second partial derivatives because that's what's actually going to be helpful to us in our case here. So consider the two variable function that we've dealt with already, our 3xy squared plus 2xy plus x squared, whose partial derivative with respect to x is already this. We've already done that. And the partial derivative with respect, actually, I'm not going there yet. I'm getting ahead of myself. So now if we were to take the partial derivative of our partial derivative now with respect to y, so now we're including this piece right here. We're going to now take the partial derivative of what we just got for the partial derivative with respect to x, but now we're going to do it with respect to y. Now you take the derivative of this thing, which is the same as what we just got above, but with respect to y. So that's where you get the 6y plus 2 from. So notice the way that we write this is we've already taken the partial derivative with respect to x, which is here, and then you take the partial derivative with respect to y. So if you were literally to multiply the denominators together, you would get dy dx on the bottom, dy times dx, which is why that's the order that you see it in right here. It really means you did the derivative with respect to x first, then you did it with respect to y. A little bit harder because it's kind of backwards. You're doing the x first and then the y, and you're reading that right to left. It's much easier in this notation, where this just simply says, take the partial with respect to x, then y, left to right, just as you would normally see it. So pay attention to the order because that can be tricky. Okay, how many different second order partial derivatives of two variable functions can you think of? Well, we can list them. We can do fxx, which means that you're going to do the derivative with respect to x and then the derivative with respect to x again. That's that one. You can do the derivative with respect to x first and then with respect to y. That one. You can do the derivative of y first, then with respect to x. Or you could do the derivative with respect to y and then y again. So there's really 4 different possibilities. All right. For our last example, let's find the 4 second order partial derivatives. Not terribly difficult. Just make sure that we are careful with this. So let's do fxx first. In order to do fxx, you now have to get fx. So fx with respect to x here, remember the only part that's changing is the x, so that's 2x, keep the y cubed. For the second part, it's 4x cubed, keep the y. And for the last part, the derivative of the x part is just 1, so it's just e to the y. Okay, over here, I'm going to do f of y, because we need both of the first derivatives before we can get to the 4 seconds. So now let's do the derivative with respect to y. Keep the x squared, but we'll change the y cubed now to 3y squared, so it's 3x squared y squared. With the second part, the derivative of y is just 1, so it's x to the 4th. And with the last one, the x is a constant, so it stays there, and the derivative of e to the y is just e to the y. So it actually is the same as that term. All right, now let's find our partials. So we can do fxx, which is the first one, the derivative of f of x first, and then with respect to x again. So if I take the derivative of 2x, that's just 2, and then keep the y cubed. The derivative of the second one, 4x cubed, that's going to be 12x squared, keep the y. Now the last piece is just e to the y. There's no x's in it at all. That's 0. There's nothing more to it. We could also have done the derivative fxy. y. So we'll go back to this one first, that's where we're starting from, and do the derivative now with respect to y. So in this case, we're going to take the 3 out to the front and multiply it. That becomes a 6. Keep the x, and now it's y squared. The derivative of the second piece, well, the y is the only piece that's there. There's no exponent, so it's just 1. So it's just going to give us 4x cubed. And then the last piece, the derivative of e to the y, is just e to the y. Okay, now let's go over to f of y. Well, we could do fyy. So do the derivative of y twice. So we're going to go back to fy, and now we'll do the derivative with respect to y again. Bring the 2 out to the front, and that's going to give us a 6. X squared stays the same. Reduce the y by 1. The second piece has x to the 4th. There's no y's in it at all. That's 0. The last piece has an e to the y, so the x is constant. And then derivative of e to the y is just e to the y. But we could also do f of y then x. So again, go back to this. Now take the derivative with respect to x only. So now we'll bring that 2 from the x out to the front and get 6. Reduce the x by 1, keep y constant, y squared. The next piece is just 4x cubed. And then the last piece, we're doing that with respect to x. The derivative of x is 1, so we get plus e to the y. Now, it's not something that we are really going to deal with all that much, but if you notice, look what happens with fxy and fyx derivatives. These two things are equal. There's an actual reason for this. Again, not something we're going to go into now. This has been plenty a long enough video, but that's how you do all of your second partials.